Welcome back, guys. My name is Marlon Etchery. I'm from the Natural and Social Science Lab at Miami-Dade Kendall campus. Today, we're going to be continuing where we left off yesterday. What we were looking at in the last video was how to solve for the oxidation states in a compound. I left you with one example. We're going to look at another example. I would like to remind you, though, before we begin, of some of the more important points that you have to be thinking about when you're trying to solve these problems. The very first thing you have to be aware of is what type of compound am I dealing with? Here we have an ionic compound. You have a metal and a non-metal component. So if they ask you for the oxidation state of phosphorus, you can simply say that phosphorus is equal to an oxidation state of -3, correct? And we know this from looking at the periodic table. So if you look at the periodic table, you'll come here and you'll see that it's in group 5A, and you'll know instantly that it's -3 because those are the charges in ionic compounds. Now, the key thing to look at when you're dealing with a compound like this is what is known as a polyatomic. Whenever you have a charge at the top, this makes this very different. Not to mention also that we have a nonmetal and a second nonmetal. So this makes this a covalent compound, but in particular, what is known as a polyatomic compound. Our approach will be the same. Whenever you're dealing with covalent compounds, what you have to do is you have to create an equation out of the chemical formula and out of the charge that's stated on the top right. Some of the key ideas to remember is that most of the time, oxygen will be equal to -2. That'll be very helpful in order to solve these problems. And then that hydrogen is equal to +1 in most cases. But do be aware, there are exceptions for each. You make sure you start looking at the rules and that you really start working on memorizing some of the exceptions. So let's create an equation for phosphate. It's 1 phosphorus plus 4 oxygens to give us a total charge of -3. So this is the equation that I've come up with from my chemical formula that I have here, correct? Next thing I want to do is I want to plug in the charges that I do know. The one charge that will help me most of the time is oxygen. I know that oxygen is equal to a -2 charge, and then I'm going to plug that in, correct? Now I can just solve this like if it was a regular math problem. Phosphorus plus 4 times -2 is equal to -3. So let's just go ahead and solve for that. 4 times -2 gives you -8, plus phosphorus is equal to a -3 charge, -3. Add 8 to both sides, and we obtain phosphorus having an oxidation state of +5. Again, that's very different from what you would see in an ionic compound. So make sure that the very first thing you do is you figure out what you're dealing with. In here, you have an ionic compound where you actually crisscross the charges of -3, and that gave you the little 3 down here, versus we have a covalent compound where that is not the situation here. And that's why you have to recall the method in order to solve for the oxidation state of phosphorus. It's potassium permanganate, which would be potassium, manganese, and oxygen. This may seem like a more intimidating problem because it's a combination of 3 elements, but it's really not. We really stick to what we already know and what we understand. We're going to create an equation out of this, and we're going to plug in the charges that we do know. So what do we have? We have 1 potassium plus 1 manganese plus 4 oxygens. And now if you recall that if there's no charge that's actually present, then you have to recall that there is an invisible 0. So we're going to set this whole equation equal to 0. Let's go ahead and plug in the charges that we do know. Oxygen, like I said, most of the time will be equal to -2. So this is actually 4 times -2. Potassium is equal to a +1. You should be able to get that from the periodic table. This is a +1 charge. It's in group 1A. And last but not least, we have our 1 manganese here. So now we can go ahead and approach this again like a regular math problem. And I could say that I have 1 plus manganese, my unknown, plus a negative 8 is equal to 0. Before you start bringing stuff over, add like terms. We have a 1 here, we have an 8 here, so I'll take care of that first. So I'll say manganese plus a negative 7 is equal to 0. Bring it over to the other side, and sure enough, we get our final solution for the oxidation state of manganese is equal to a positive 7. So this should be your final answer. Do not be intimidated if you see a larger problem. Just stick to what you already know and what we've been practicing. So, if you were given a compound like KO2 and you were told to solve for the oxidation state of oxygen, you would be very tempted in this case to simply say that oxygen is equal to negative 2. But if you were to plug this into equation, you would see something very interesting, and this is what you should try and do. 1 potassium plus 2 oxygens should be equal to an overall charge of 0. You plug in the charges that you already know. We know that oxygen should be negative 2, but in this case we're going to see that it's actually not. We know that potassium is always positive 1, so then we plug in, and if you were to resolve for this problem, you would end up getting that negative 4 plus a positive 1 gives you 0. You resolve for this, and you get that negative 3 is equal to 0. Clearly, that's not correct. And the issue is not with my potassium. If you remember the rules and you start looking at them carefully, you'll realize that group 1A elements are always positive 1 charge. What's the one that's not always negative 2? Oxygen. We said in the beginning in the previous video that there are exceptions to it. This is one of those moments, and this is how you would realize that you're dealing with an exception. In this particular case, once I realized that something is wrong with my compound, I would actually go back to my initial equation and I would solve for the charge of, or the oxidation state of oxygen here. That would be my approach. Now, when I try to solve this problem, the only charge that I would plug in would be the charge of potassium. So I'd have 1 times a positive 1 plus 2 times my unknown is going to all be equal to 0. Start to solve for this. I have 1 plus 2O, 2 times O I should say, is equal to 0. Correct? Let me go ahead and put that in red so you can differentiate that this is oxygen and not a regular 0. Minus 1, minus 1. So now I have 2 times oxygen is equal to negative 1. How do I solve for this? I simply divide both sides by 2, and I get my final answer. Then in this particular case, oxygen is equal to a negative 1/2 oxidation state. This is one of the exceptions I was talking about that you have to be careful for when you're doing these problems. So do be aware. Oxygen is typically equal to negative 2, but in some cases, it can actually be equal to a negative 1/2. Thank you.